Good morning, everybody. Let's go over some announcements here. Remember, the exam is next week on Tuesday, so the homework assignment will be due on Monday at noon. The solution will be visible right then at 12 o'clock. We'll have our test in class on Tuesday. If you want to take a look at the formula sheet that I'm going to provide, it's already loaded on MU Online. It's the same as the one that was there during the first exam, so nothing will have changed with that. You're not permitted to prepare your own formula sheet. Everything you need will be on that equation sheet that I provide. Today we're going to be talking about some additional, more complicated applications of the momentum equation. We'll also look at a couple of the homework problems that are in this assignment number 10, just to introduce some of the key ideas as it relates to flow-through pipes. So are there any questions on the announcements? Yeah.
So the exam will cover everything up to today?
That's right. Yeah. Other questions? Okay. Just to get the momentum juices going in your mind, just to get some momentum. Oh, that's the worst. Let's consider that we have some fluid with a specific gravity of 2.0. So that's what's defining the density for us. And we have a black box where we don't necessarily know what's going on inside of here. It's probably a series of veins and bends. But what we do know is that we can draw a control surface around this box where a change is occurring. And it doesn't really matter what's happening inside so long as we keep track of the flow in and the flow out. That's all that's going to cause any forces that have to be applied to hold the system steady. So you can see that there are 4 separate streams. And for stream 1, we know the flow rate on a volumetric basis, the velocity. Stream 2, flow rate, velocity, and I guess we also, in addition to knowing the magnitude of the velocity, we know the direction by the arrow that's indicated. Stream 4, we know the flow rate and the velocity, but stream 3 only has the velocity defined. It doesn't tell us the flow rate. So what you'll need to do is use the continuity equation to tell you what's the flow rate at 3. And since we don't have any information given in the problem statement or in the drawing about accumulation inside of the control volume, so in other words, in the absence of any kind of like a flywheel being specified or a tank where flow is being stored, you can assume that the flow in and the flow out are equal. And so that'll be the continuity relationship you use to solve for Q3. And then once you have Q3, then we'll consider the momentum part of it. In other words, what force is required in the x direction to hold it steady, and what force is required in the y direction to hold this black box steady. I guess we should have just been able to look at it and know that there was no force in the x direction. I mean, that's in retrospect kind of clear from inspection, right? That if you have one of them's coming in from the left at 60 meters per second and the flow rate is 0.15, well, this stream coming from the right has twice the flow rate but half the velocity. So they're going to be just spraying each other and canceling out anything that's happening in the x direction. So, but don't just put that, don't do just kind of like a reasoning on an exam or something like that. You'd actually want to crunch the numbers to prove it. You know. But the numbers do prove it, that you know, if we have the mass flow rate at 4 and at 2, and then there's no flow out in x, just in. So this term cancels, and then You'll notice that here I'm saying the sum of the mass flow rates in, velocity in, and x. I guess just out of laziness, I don't bother to usually write this summation term, but I think as I was walking around, most of you recognize that if you have more than one thing coming in, then it's just the effect is additive. So where we have two streams that are going in, they're both going to have this negative sign applied to them. So it's minus mass flow rate at 4, V4, minus mass flow rate at 2, V2. And then since one of them, that stream 2, is to the left, then it's going to pick up the minus sign due to the direction of its velocity. And since it was a minus of that term to begin with, then that's why it ends up canceling out, is because both of them were inflows, so they both get this minus sign, but then one of the inflows was to the left. So the two streams cancel each other. Okay, we didn't have to apply continuity equation in the x direction because the flow rates were defined directly, and we could calculate the mass flow rates just by knowing the unit weight, the specific gravity of 2.0. Any questions from the x direction? All right, now vertically, we don't know Q3, and so this is where we apply in equals out. In is 2 and 4, out is 1 and 3. So whatever doesn't come out at 1 of these two jets, all of the fluid that's coming in, some of it comes out at 1 and the rest goes out at 3. So the balance of the flow rate at 3, here's where I'm calculating that. Mass flow rate 1 we know directly because the volumetric flow rate is specified, but the mass at 3, the mass flow rate at 3 is going to be the two in streams minus the other out stream, and that tells us what balance remains that has to come out at 3, 700 kilograms per second. Otherwise, there would be some accumulation inside of that black box. So then, in the vertical, there's only outflow, no inflow. So if we look at the overall equation here, there's only outflow, no inflow. So the second term it won't apply. But then the two outflows have an additive effect. And so we just combine M1V1 with M3V3. And of course, since stream 3 is downward, we have to give a negative to the 15 meters per second velocity there. So remember how we said in retrospect it's obvious that horizontally it cancels out. But is it also makes sense conceptually why the force has to be down? Let's consider that. We've got 700 kilograms per second going out through the bottom. And what was the mass flow rate at 1? 200. All right, now the velocities are also different, but there's a lot more fluid going down than up. And so just think about if you had a stream that's coming in, you got to push it down to change its direction. So on net, we're going to have to apply an external force downward in order to make that change in direction occur. Where it was all horizontal before, and now a little bit of that stream is going upwards, but the far greater portion of the incoming fluid is directed downward because it's 700 kilograms per second versus 200 kilograms per second. Now we also have to multiply the velocities, but the velocities are relatively close, 15 and 20 meters per second. So the far greater difference is that we've got a big mass flow rate going down. So always kind of ask yourself if the directions that you've calculated by going through the calculations, if it makes sense. In this case, it does. And so always really clarify the direction intended by that negative sign. So I've given the negative sign, which implies I mean downward, but then I eliminate any possibility of doubt by saying you have to push down to hold the system steady. All right, any questions on this example with the black box? Okay, till now, the left side of the momentum equation has always just been some external force that we're applying to hold the system steady. that's going to change a little bit when we have fluid that's flowing through a pipe. So you have a homework, actually 3 homework problems that are similar to this, where you have a nozzle that's changing the velocity, but then not pictured here, this is a pipe that continues beyond what's pictured. And so the fluid is coming from some unspecified location on the left. The fluid is moving along under pressure, and then it contracts the diameter, which increases the velocity, and then we have it exiting at a jet. What's the fluid pressure inside of a jet? It's 0 gauge. So it's the same pressure as the surrounding atmosphere. And so this is one of those problems where when we've had nozzles in the past, we've used Bernoulli's equation to tell us, well, if we know the velocity at both locations and we know the pressure at 2, we can calculate the pressure at 1 based on Bernoulli's equation. So there's also a momentum effect happening. It's not just a change in pressure that occurs, which is what Bernoulli's equation models, but the momentum equation is saying that we're going to have to apply some force to hold this system steady. But it's not just the external force that would be applied here at this flange to hold the system steady, because the pressure that's in the pipe is acting on what's ever inside of our control volume. So remember, our approach with momentum problems is we draw some dashed line that represents the control surfaces, and inside of the control surface is the control volume. And so anything on the outside of the control volume is considered as an external force, including the pressure in the pipe acting over some cross-sectional area. So in other words, the water in the pipe that's to the left of the control surface is pressurized, and it's acting over the cross-sectional area of the pipe. And so P1A1 is a force that we're going to have to account for on the left side of this equation. So you'll notice that here the momentum equation, where we are saying the sum of all the forces, well, one of those forces is an external force applied at the flange, F of x, but then the other force that's acting on the system, besides that one that we have to apply to hold it steady, this other force that's relevant is P1A1. All right? Now, it's also going to have direction. And so the direction, since we cut this pipe, and the pressure is on the left acting towards the right, then that effect will be positive on the left-hand side. If the nozzle's direction was reversed and we were cutting some location where the pressure was acting from the right to the left, then this pressure term would be negative. And we'll look at an example from the homework where that is the case. But before we do that, let's actually calculate the momentum effects that are occurring here. You'll notice that the mass flow rate out and the mass flow rate in are the same, so I've just consolidated that into a single m dot term. So, we can group together mass flow rate out and mass flow rate in, and so all the difference is just related to the velocity out and the velocity in. All right, so with this problem, what you'll need to do is, number 1, apply the flow rate and the diameter, which will give you the area. Find V1 and V2. So let me write this on the board. All right, so first step, find A1 and A2 from the given diameters. Next step, find V1 and V2 with V equals Q divided by area. Okay, third step is Bernoulli equation. Bernoulli equation to find P1. And then, once we have Bernoulli's equation, you can substitute it into the momentum equation. I guess we're going to need to know the mass flow rate, and then momentum, to find the only remaining unknown will be f of x, which is what external force do we have to apply at the flange to cancel out the two momentum issues. There's the flow that's changing velocity. That's going to be one effect, but then the other effect is this pressure that's acting from the left towards the right on our control surface. And I know it's strange to think of that, you know, this is an imaginary control surface, but yet we're pretending as though it's a force that's actually applying on this imaginary control surface. It's only imaginary in the sense that where you choose to locate the control surface can change, but regardless of where you put this control surface, there is pressure in that pipe, and it does affect the force that has to be applied. So it's how we can account for it, is by putting the control surface and then just treating this pressure as though it's an external force on the left-hand side of the equation. So you've got the step-by-step on the whiteboard there. Let me give you a minute to calculate that, and we'll check and see if we're all on the same page. On the homework, I tried to make a couple of the problems where you were actually given the cross-sectional area, because it gets pretty tedious always calculating the area every single time the diameter is given. I get that you already understand A is pi d squared divided by 4, so hopefully that won't be something that's just always a fact of life. But in any case, the flow in and the flow out are equal, so we can get the two velocities. Then Bernoulli's equation tells us the pressure in the pipe. Now, you know, I round off on paper here. Sometimes what I've been doing more recently is I've been, you know, when I write this down, I'd say like 38.2 ... just to indicate that there's some more digits there in the calculator, and I'm keeping all that precision because it's important, especially when you're squaring things. So I think if we're working on an exact basis and don't do any rounding off, it should be the pressure in the pipe is 720 kilopascals, I believe. And so then the momentum equation, when we account for the pressure acting as an external force from the left, acting towards the right, so it's a positive effect, pushing to the right on the system, then it should be that the force we have to apply is to the left. So we're resisting both the acceleration of the fluid, so even just the momentum aspect of things means we're having to push to the left because of the fluid speeding up. But then that pressure thing also means that we have to resist even harder at the left. And so the force direction was just indicated to the right in the sketch here. And so I have the negative, meaning in the opposite direction, assumed by our standard convention, being positive to the right is x, and then also clarifying with the statement that the force must be applied to the left to hold the system steady. And also, not just direction I've indicated, but also because remember how sometimes the questions are asking what force is the water applying to the system? Like what force is the water applying to the nozzle would be different from what force do you have to apply to the nozzle to hold it steady. So this is just specifying the direction of the force and also which force we're talking about. We're talking about external force required to hold the system steady. Okay, so everybody understands what to do if you're cutting a pipe that has water flowing through it and the pipe continues to the left. It's not just there's some mystery fluid, and it's not a jet of water that's going into this nozzle. It's that the pipe continues to the left. And so let's look at some related homework problems. In your assignment, you have this one. And this is water that's flowing out of a nozzle, but the pipe does not continue infinitely to the left. What's causing the flow outward is the fact that inside of our control volume, this syringe is pushing the fluid out. And so if you draw your control volume so that everything inside of this nozzle is inside the control volume, there isn't a P1A1 that's going to have to be added externally. So in other words, since the pipe doesn't continue, the force of X that this is going to be asking for will be the difference between the piston, which is pushing to the right, and the pin that's resisting it to the left. So I wanted to clarify that in this one, don't just think that because there's a nozzle, there's always going to be a P times A effect, because in this problem there's not. Okay? But there are a lot of other similarities though. You know, Bernoulli's equation to find the pressure, because you're going to need to know the pressure inside here to know what force has to be applied at the piston. You know, there is a relationship between the force of the piston is the pressure of the fluid times the area of the piston. So Bernoulli's equation still will be important to find out F piston. All right, here's another one. Very similar to today's, right? So I don't think that this one will be too much trouble. The areas are given directly. It's just asking the force at the flange that has to be applied. Now, consider that this is a cross-sectional view, and the pipe itself is circular, and this flange goes all the way around it. So don't be confused by the fact that you're seeing the flange at the bottom and the top and think, well, is it two forces that are applied? No, it's just a single net force that's being applied, and it's being applied in a distributed way all the way around that ring. We're just finding what single force would be required to hold the system steady when we know the velocity is going to be increasing and that the pipe continues, not pictured, to the left. So this is very closely related to today's example. Feel free to chime in if you've got any questions. This is the tricky one. This combines some of the ideas that we addressed with the black box problem today. So this is a combination of the black box, but then there's also the pressure times area thing happening, because these pipes continue. I think the drawing is implying that the pipes continue with that kind of curved, I don't know, whatever the shape of that is, that means that the pipe continues. So there's water coming in at 1, going out at 3, and the rest of it's going out at 2. So you're going to use the continuity relationship to find out the in equaling the out. You know, I think in the problem statement only 2 of the streams are defined in terms of the Q, and 1 of them is left undefined, and so in equals out here. There's no tank that storage is accumulating in. The areas are given, so you can find the velocities with the Q. So again, that's similar also to the black box problem. But then what's different is, think about in the x direction. What is our momentum equation going to look like in the x direction? You know, the general form of the momentum equation, sum of the forces in x is equal to the sum of the mass flow rate out, velocity out in x, minus the sum of the streams, which are mass flow rate in, velocity in x. So in the horizontal direction, we've got 1 out and 1 in the horizontal direction. And then there's going to be 2 pressure effects, though, because we're cutting this pipe both on the left and on the right. So I don't want to spoil all the thought that you've got to do to solve this one. But what I'll say is that it doesn't matter what direction the flow is. So here at 3, even though the flow is to the right, the pressure is still pushing to the left. And so, you know, there's going to be some effect of the pressure at 3 times the area at 3 because we cut this pipe. But that force, that external force, is acting to the left, whereas here it's acting to the right. So that's important because of what it means to the left-hand side of that equation. And I'll remind you, what did it do to the left-hand side of the equation when we worked on this example? Well, we put P1A1 on the left side. Because, and it was positive P1A1 because the force was to the right. All right, so those are all the hints I want to give you for now on the homework assignment. If you have any questions, though, feel free to let me know. Let's do one other thing, and that's talk about an application of the momentum equation that I think is kind of interesting. We've talked about the jet water boots things, and we saw the video of the flyboard air, the French guy who flies around. Actually, he crossed the English Channel recently. Did anybody hear about that? He had some sort of a floating platform halfway so he could get more fuel, but he flew from England to France on the little flyboard air that he developed. One application of the momentum equation is the landing craft air cushion. This is a Marine Corps toy for invading other countries, like a beach invasion. Instead of swimming ashore, why swim when you can use a hovercraft? So this is a hovercraft, and it's pretty big. It's really huge. It's 26 meters long, 14 meters wide, and so you can see that they can fit a single tank, or I think 4 armored personnel carriers at a time. So it has the capacity to carry 185,000 kilograms, and it's really fast too. I think its top speed is maybe classified, I don't know, the cat's out of the bag. It can do about 80 miles per hour, and it just burns an enormous amount of fuel, 1,000 gallons an hour. So you really wouldn't want to pay the fuel bill on that one.
We do pay the fuel bill on that.
Yeah, that's true, we do. Yeah, good point. You wouldn't want to be the only one. It's good that it's split among 300 million of us. That takes some of the pain out of it. You wouldn't want to drive it to school. Well, maybe you would want to drive it to school. All right, let's watch a little video of the LCAC. This video was commemorating their first time using a renewable fuel in an LCAC. It's, I guess, a kindler and gentler Marine Corps when they're using algae-derived fuels to invade. So the way it works is there's an air cushion, a very thin air cushion. So previously, before the air was being directed downward, it was just resting on posts. But now this flexible boom that goes around the edge, the curtain, is kind of directing the air cushion downward. Now you can see it's got a tank on there right now. James, you ever been on an LCAC?
Unfortunately not.
No? All right. So there they go. Doesn't look that fast. They, I guess, probably take a little while to get up to speed. But the cool thing is that they steer it with, maybe the view is better here. You see these ducted, they're like air ducts, and they rotate around. And so the main propulsion is at the back. They've got these big fans, and so that pushes it forward. But then the way that they steer is by redirecting air through these ducts on the top. So we can see that when they want to turn it, watch what the duct does as they kind of swing around. Okay, so I think you get the idea. This is momentum in action here. They're using the air, pushing the air at a faster velocity than it came in, and by pushing air out of the way, it's generating thrust. Enough thrust to overcome the wind resistance and to overcome the inertia that it's initially at rest. So there's an imbalance of force which allows it to accelerate. There they go. All right. All right, so I have an in-class exercise, a handout for you, where we're going to work through a couple of questions here. Now, I want you to get in the habit of being able to identify where the control surfaces need to be to solve a problem. So, draw a little sketch of the LCAC, and then where is the control surface going to go, where you're keeping track of the flow in and the flow out. And then remember, force is pressure times area. So what is the pressure under that skirt got to be? The like the flexible rubber ring at the bottom. What does the air pressure have to be in order to support how heavy it is? 185,000 kilograms. You know, by contrast, how many kilograms is a semi-truck?
Probably
35,000? 30,000 maybe? Because semi-truck usually is 80,000 pounds maximum load. So this is way beyond that. You know, we're talking 5 semi-trucks at least, maybe more. So very heavy. So we need to know what pressure has to be achieved if it's from the plan view. Looking down from above, the dimensions are 26.4 meters long, 14.3 meters wide.
Now, are there like holes up above the skirt, or
What?
the mass times the mass flow rate times velocity, and figure out where that would be at?
The mass times velocity is, you know, the side view here, the propellers that it's showing. So to get forward movement, it's the velocity coming off of the propellers that drives it forward. But it is the air that's directed downward that allows it to float on top of the surface rather than floating in the water. So it goes a lot faster because it's riding on a cushion of air. Now, if they run out of gas in the middle of the ocean, it doesn't sink. It has buoyancy. It's just that it's not going to go nearly as fast if the water is up in the hole than if it's floating on top of an air cushion.
You ever seen those big inflatable balls that